Good day, everyone. Today, I'll be presenting a comprehensive analysis of LinkedIn's application maintenance and monitoring practices. My name is Marvic Solares, and this report is part of SAM 413 or System Administration and Maintenance. Over the next 10 minutes, we'll explore how LinkedIn, one of the world's largest professional networking platforms with over 900 million users, manages its complex infrastructure, ensures data security, and maintains system reliability. Let's begin with some context about LinkedIn as an application. LinkedIn is a cloud based, globally distributed platform that operates 24/7 across multiple data centers worldwide. From a system administration perspective, LinkedIn presents unique challenges. It handles billions of daily transactions, stores petabytes of user data, and must maintain 99.99% uptime to serve its global user base. The platform runs on microservices architecture, utilizing technologies like Java, Kafka for real-time data streaming, and Voldemort for distributed data storage. Understanding this technical foundation is crucial for appreciating the maintenance and monitoring strategies we'll discuss today. This presentation will examine LinkedIn through three critical lenses of system administration. First, we'll explore the advantages of LinkedIn's architecture, particularly focusing on data security, scalability, and upgrade mechanisms. Second, we'll address the realistic challenges and disadvantages that come from managing such a massive platform. And finally, we'll discuss the practical actions and protocols LinkedIn implements during system failures. This balanced approach will give us insights in both the successes and ongoing challenges of maintaining enterprise level applications in today's digital landscape. LinkedIn's architecture excels in three key areas that are fundamental to modern application maintenance. First is strong data security, protecting millions of professional profiles and sensitive career information. Second is scalable massive data handling, the ability to process and store enormous amounts of data while maintaining performance. And third is seamless system upgrades, the capability to update and improve the platform without disrupting user experience. Let's examine each of these advantages in detail. Data security is LinkedIn's top priority, and they've implemented multiple layers of protection. Starting with privacy settings management, LinkedIn provides granular controls that allow users to customize who sees their profile, connection, and activities. These settings are regularly reviewed and updated to adapt to evolving privacy concerns. For data transmission and storage, LinkedIn employs end-to-end encryption. All data in transit uses transport layer security or known as TLS, which is the same technology banks use. Stored sensitive data is protected with AES 256-bit encryption, which is also one of the strongest encryption standards available. Their messaging system is particularly secure, ensuring professional communications remain confidential. Next, in terms of global regulatory compliance, LinkedIn adheres to strict international standards including GDPR for European users and CCPA for California residents. They support data portability, allowing users to download their information and honor the right to be forgotten for data deletion requests. Finally, multi-factor authentication adds an essential security layer. Users can enable two-factor authentication through SMS or authenticator apps. The system continuously monitors login attempts, alerting users to suspicious activities. This multi-layered approach significantly reduces the risk of unauthorized access. LinkedIn's ability to handle massive data is truly impressive from a system administration standpoint. The platform processes over 200 billion data points daily from user interactions, searches, job postings, and content engagement. To manage this scale, LinkedIn uses a distributed architecture with multiple specialized databases. They employ Apache Kafka for real time data streaming, processing millions of events per second. For storage, they use a combination of technologies: Voldemort for distributed key value storage, Espresso for online transaction processing, and Venice for derived data storage. This hybrid transaction allows them to optimize for different data types and access patterns. Their data handling includes sophisticated indexing and caching strategies. The search functionality, which needs to return relevant results from billions of profiles in milliseconds, uses distributed search indexes that are constantly updated. LinkedIn also implements data partitioning and sharding to distribute loads across multiple servers, ensuring no single point becomes a bottleneck. LinkedIn approach to system upgrades demonstrates excellence in maintaining service continuity. They follow a continuous deployment model, pushing code changes multiple times per day without users noticing any disruption. The key to their success is the use of canary deployments and blue-green deployment strategies. With canary deployments, new features are first rolled out to a small percentage of users, allowing engineers to monitor performance and catch issues before full deployment. Blue-green deployment maintains two identical production environments, allowing instant rollback if problems arise. LinkedIn also implements comprehensive automated testing, including unit tests, integration tests, and performance tests that run before any code reaches production. They use feature flags to enable or disable functionality without deploying new code, providing precise control over new feature releases. Additionally, they schedule major infrastructure upgrades during low traffic periods and communicate planned maintenance windows to enterprise customers. This proactive approach minimizes impact on users who rely on LinkedIn for recruiting and marketing. However, managing a platform of LinkedIn's scale isn't without challenges. Despite robust security measures, data security risks persist. The massive data handling capabilities we discussed also present significant challenges in terms of cost and complexity. The system upgrades, while generally seamless, can introduce unforeseen issues. It's important to acknowledge these disadvantages to understand the complete picture of application maintenance at this scale. Despite LinkedIn's strong security infrastructure, several risks remain. The platform has experienced data breaches in the past, including a notable incident in 2012 and subsequent data scraping incidents. While the platform itself may be secure, user behavior remains a vulnerability. Phishing attacks targeting LinkedIn users are common, with scammers creating fake profiles or impersonating recruiters. The sheer amount of data LinkedIn stores makes it an attractive target for cybercriminals. Professional information, email addresses, and career histories are valuable for social engineering attacks. Account takeovers, though relatively rare, can lead to reputation damage and unauthorized access to company networks if affected users have shared corporate information. From a system administration perspective, maintaining security at this scale requires constant vigilance. Security patches must be applied quickly, but testing them across a distributed system is complex. third party integrations while extending LinkedIn's functionality also introduce potential security vulnerabilities that must be continuously monitored and managed. The same massive data infrastructure that enables LinkedIn's functionality also presents significant challenges. Storage costs are enormous. Maintaining petabytes of data with redundancy and backups require substantial investment. As the platform grows, storage needs increase exponentially. Data consistency across distributed systems is an ongoing challenge. With data replicated across multiple geographic regions, ensuring all users see consistent information while maintaining performance is technically complex. The COP theorem forces trade-offs between consistency, availability, and partition tolerance. Regarding system upgrade issues, even with careful planning, problems can occur. Performance degradation sometimes follows major upgrades as unexpected bottlenecks emerge under real-world load. Dependency conflicts between microservices can cause cascading failures. Database migrations are particularly risky. Moving or restructuring data while maintaining service availability requires meticulous planning. Backward compatibility is another concern. As LinkedIn evolves, they must maintain API compatibility for thousands of third-party integrations while simultaneously moving the platform forward. This creates technical debt that accumulates over time. When system failures occur, LinkedIn follows a well-defined incident response protocol. Their first priority is detection. They use comprehensive monitoring tools that track system health metrics, error rates, and performance indicators in real time. Automated alerts notify on-call engineers immediately when their shards are breached. The incident response process begins with initial triage to assess impact and severity. High severity incidents affecting many users trigger a major incident response, bringing together engineers from multiple teams. Communication protocols ensure stakeholders are informed. Status pages update users about ongoing issues, and internal communication channels coordinate the response. For resolution, LinkedIn employs several strategies. Immediate mitigation might involve routing traffic away from affected systems, increasing resource allocation, or activating backup systems. Root cause analysis happens in parallel, with engineers investigating logs, metrics, and distributed traces to identify the underlying cause or issue. For post-incident, LinkedIn conducts blameless post-mortems, where teams analyze what happened, why it happened, and how to prevent recurrence. These learnings feed into improved monitoring, better testing, and architectural changes. They maintain a public engineering blog where they sometimes share lessons from major incidents, contributing to the broader tech community's knowledge. In conclusion, LinkedIn exemplifies both the capabilities and complexities of modern application maintenance. Their robust security framework, scalable data infrastructure, and sophisticated upgrade mechanisms represent industry best practices. However, the challenges they face, security threats, data management, complexity, and upgrade risk, remind us that system administration at scale requires continuous improvement and vigilance. The key takeaways are: first, security must be multi layered and continuous evolved. Second, scalability requires architectural planning and significant investment. Third, seamless operations demand rigorous processes, automation, and skilled teams. LinkedIn's approach to maintenance and monitoring offers valuable lessons for anyone involved in the system administration, regardless of scale.